Hi everyone, welcome you all in the video course on Geotechnical Earthquake Engineering. I am Nitin Singh Arora, Assistant Professor in Civil Engineering Department at Chandigarh University. For any queries, you can contact me on nitinarora.civil@cmail.in. Before going to the course contents discussions, let's have some discussions on course objectives and course outcomes. First course objective is to understand the effect of earthquake on soil structures and to design earthquake resistance geotechnical structures by using different codal provisions. Then outcomes: after the completion of course, the student will be able to design or will be able to see all the aspects of earthquake and ground response, and they would be able to analyze and quantify earthquake hazard in terms of ground amplifications, deformation, liquefaction phenomena, be able to design the earthquake resistant structures by using codal provisions. Let us first see the course details and course contents for Geotechnical Earthquake Engineering video course. Here are the course outline in total. This course on Geotechnical Earthquake Engineering introduces the fundamental concept of earthquake engineering related to geotechnical problems, principle of earthquake, wave propagation, dynamic soil properties, and the very important phenomena liquefaction and seismic design of various geotechnical structures like retaining walls, waterfront retaining structures, slopes, earthen embankments, anchors, etc. This course focuses on seismic hazard analysis, which includes both probabilistic and deterministic seismic hazard analysis, followed by the response analysis. In continuation with the course outlines, this course also focuses on the behavior of various geotechnical structures such as shallow and deep foundations, retaining structures, slope ground anchors, waterfront retaining structures, reinforced soil tailing dams due to earthquake loading are discussed with reference to the codal provisions, right? Then this course material on geotechnical engineering will be very useful for the post-graduation students, researchers, teachers, practitioners, and all. In the course content, we have basically divided this course, the full geotechnical earthquake engineering course, into three parts. In first part, we'll be discussing or we'll be learning about the earthquake engineering, that is the basic vibration theory, engineering seismology, strong ground motions, how these waves will propagate in different mediums of earth. Then in second part, we'll be studying about the soil behavior or soil properties under dynamic conditions, seismic hazard analysis, and then how site will respond to the waves, to the dynamic conditions. Then we'll do the site response analysis. Finally, in second part, dynamic soil structure interaction, very important, we'll be going to discuss in this course. Then in the third part, we'll be discussing about the applications of earthquake engineering to various geotechnical problems. Like we face very serious problems in design of retaining walls, foundations, anchor piles, tailing dams, landfills, slopes, waterfront retaining walls, sea walls, reinforced soil walls, liquefaction. Liquefaction is a very uh, important phenomena to be discussed, right? It is a very serious geotechnical engineering problem. Then finally, we'll be doing hazard mapping. As we have seen in the course content, it is being divided into three parts. First part is related to the earthquake engineering part, and second part is related to the soil properties, dynamic properties, or how soil will behave in dynamic conditions, how the waves will propagate. So for that, you will be having some prerequisite for this course content. The very first important prerequisite which is mandatory for this course is soil mechanics or geotechnical engineering. Then next, which is also an important prerequisite for this course, is soil dynamics. You should be having some knowledge that how the soil will behave in dynamic conditions. Now let us see what are the major references we'll be following for this course. Here is the list of the books. There are some other references also we'll be discussing as well. First is Stephen L. Kramer, Geotechnical Earthquake Engineering, published by Britten's Hall. It is one of the finest book which is available on this subject, which is being originally published in 1996. Later on, we got 2007 version, which is also being available. Second reference is of Geotechnical Earthquake Engineering Handbook, which is basically will use for design aspect. First, it was being published in 2002 by McGraw Hill in New York. Third reference is of Professor Ikyu Tohata, Geotechnical Earthquake Engineering, published by Springer. Then we have fourth reference of Professor Kenji Ishihara, Soil Behavior in Earthquake Engineering, published by Oxford University Press, USA. Then we have one more reference for soil dynamics of Professor Shamsher Prakash, published by McGraw Hill. So we'll start from the introduction of geotechnical earthquake engineering, in which we'll be discussing the need and importance of this course. Now you can see from these pictures showing the devastating effect of earthquake due to failure of structure. And someone has rightly said the earthquake never kills, but the damage due to structures during earthquake due to incorrect or insufficient design and construction that kills. Here is the next slide, which depicts the devastating effect of earthquake due to failure of soil beneath. From these pictures, you can very well see the structure is safe, but it has settled down by huge amount due to failure of ground beneath the structure. In this slide, we can see the devastating effect of earthquake due to landslides and rock slides. Here are the pictures which is being taken from Sikkim during 2011 earthquake of landslides and rock slides. Here comes the next topic, principal types of earthquake damages. So there are basically two types of damages. First is in the category, first category will be the direct damages because of earthquake, and second will be the indirect damages. In the direct damages, we have structural damage, which is being caused by excessive ground shaking, strongly influenced local conditions. Then ground shaking shakes the structure constructed on the ground, causing them to collapse. Then we have one more type which is due to earthquake is liquefaction. In liquefaction, the soil beneath the structure for a while it turns out to be a fluid mass. It converts in the fluid mass for a while, which causes damage to the structure, which causes excessive settlement to the structure. Then landslides, which is being triggered by the earthquake waves or the vibrations. Then the retaining structure failure because of the excessive pressure on the retaining structure, the damage of anchored wall, sheet pile, other retaining walls and sea walls. Then there are some indirect types of earthquake damage like fire. Fire is an indirect result of earthquake triggered by broken gas pipelines and other lines. Then we have one more indirect damage because of earthquake, that is tsunami. Large waves created by the instantaneous displacement of sea floor during the submarine faulting. In this slide, we'll discuss the factors on which this earthquake damage depends. The first factor is the size of earthquake. If the size of earthquake is large, then the damage to the mankind or to man-made structures will be more. If the size of earthquake is small, then the damage will be less. The second factor is the distance from the focus of earthquake. So if the distance is large from the focus of earthquake, the damage to the man-made structures will be less. Or if the distance is less from the focus of the earthquake, the damage will be more. Third factor is the properties of material at site. That means the soil conditions, the locally available soil conditions on which the structure rests. So if the soil is hard or rocks are available or foundation is being established on the rock, so the damage will be less. If the structure is being established on soft soil, then the damage could be more. Then last factor is nature of structure in the area. That means the material by which that structure is being manufactured or is being made. The structure can be a RCC structure also, a steel structure also, or timber structure also. So the steel structures will be having less damage due to earthquake as compared to timber structure and RCC structures. As steel structures is being designed as a ductile material which is having a capability to absorb the shocks or vibrations. Now, in this slide, we'll be studying ground shaking in detail. First is frequency of shaking differs for different seismic waves. High frequency body waves shake low building more. Low buildings means the low rise buildings, single story or double story buildings. Low frequency surface waves shake high buildings more. That means high buildings, the high rise buildings more than 3-story, 4-story, 5-story buildings. So they are more vulnerable to damage if the frequency of earthquake is low. Then intensity of shaking depends on the type of subsurface material. Subsurface means on which the foundation is resting. That can be a hard strata also or a loose strata also. We have already discussed. It will depend upon the subsurface material. For loose strata, the intensity of shaking will be more. For hard strata, the rock type strata beneath the structure, the intensity of shaking will be less. Then about unconsolidated material which is not being consolidated yet. So unconsolidated material basically amplifies. So it amplifies the shaking more than the rock. So if the structure is resting on the hard strata or the rock strata, so it will definitely gives the more stability to the structure. Then building respond differently to shaking depends upon construction style and material. Construction style means the shape of the building will also be like one of the factor which respond differently for shaking or to shaking. Or secondly, the material means like steel structures are more ductile than RCC structure or timber structure, so they have more ability to take shock waves as compared to the rigid structures like RCC structure. To RCC structure, we have added steel. So more steel leads in the RCC structure leads to more ductility. But as compared to the steel structures will be having better shaking resistance as compared to the rigid RCC structure. Then we have given the example like wood more flexible, holds up well, earthen material, unreinforced concrete, very vulnerable to shaking. In this slide, we are going to discuss liquefaction. What is liquefaction? It generally occurs in loose and saturated sand. So what basically happens is the grain structure of the soil, it collapses. Pore water pressure, the water which is present in the pores of the soil, the pressure which is being created by that water is known as pore water pressure. There will be a increase in pore water pressure that leads to the decrease of effective stress. As we all know, there is a relation between effective stress, total stress, and pore water pressure. Effective stress is equal to total stress minus pore water pressure. So total stress remain constant. If the pore water pressure will increase, that leads to decrease in effective stress, and that further decreases the strength and stiffness of soil beneath the structure. That leads to the sinking of the structure in the subsurface. So for a very small period of time, that soil mass or substructure or subsoil is converted into liquid or a fluid. There will be like shear strength of the soil beneath the structure become very less or nearly equal to zero because of the increase in pore pressure. That leads to the effective that leads to the decrease in effective stress. Further, the strength and stiffness will decrease. So liquefaction is basically a combined phenomena in which there will be a combination of loose soil, that is the cohesionless sand. The soil should be cohesionless or loose in nature. It should be saturated also. Then certain frequency waves of earthquake, when it comes, it leads to the collapse in grain structure. So this is the whole phenomena of liquefaction in which the soil beneath the structure turns into fluid for fraction of second. As we have discussed the liquefaction phenomena in the previous slide, Here are the pictures showing the liquefaction failure of Fukui in 1948 earthquake. Termed liquefaction, the strength of soil it reduced often dramatically to the point where it is unable to support the structure or remain stable. So this is the picture in which structure is being designed properly. This superstructure is being designed properly to withstand the load, but the soil which is beneath the structure has shown the failure in liquefaction during the earthquake. That soil has shown that there is a reduction in soil strength for a small period of time during the earthquake. And now we have come to an end of this lecture number 1 of the series. Here are some of the review points of today's lecture. So we have started our discussion from course outlines. Then we have discussed about course contents. Next, we have discussed some of the mandatory prerequisite for this course. You are required to study geotechnical engineering first before continuing this course. Then we have discussed some of the important resource, books, references of this course. Then we have started our discussion of the subject from effects of earthquake. Here we have studied the various effects like devastating effect of earthquake due to failure of structure, devastating effect of earthquake due to failure of soil beneath the structure, and failure of landslides and rock slides. Then then we have discussed principal types of earthquake damages, direct damages because of earthquake, indirect damages due to earthquake. Then factors on which earthquake damage will depend. Then we have discussion on ground shaking phenomena and soil liquefaction. Thank you so much for attending this lecture number 1. We'll be continuing our discussion in lecture number 2 with our further course contents. Thank you so much.